If there is some version of basically the region I get is I get knocked out. I lose all the lunch and then for about a couple of minutes. I have no idea what happened.
So it looks like everybody's in class, nobody online.
Like short-term memory loss almost. Big losing. The other, I am always fully aware.
No one's online.
Well, the other two times I don't remember which one was in order. But
By the way, you still have 4 minutes. Continue chat. Sure. Not time yet.
And big wooden steps. So I seated at the very top of the steps and fell down.
It's gonna get in front of them.
Instead of there. I finished having my seizure at the bottom of the steps. Mine also seems to occur in the afternoon or evening. But thankfully, they've all been just like chilling, yeah. So I have, which is kind of surprising because my house does have a lot of stairs as well. It's got 4 stories.
Oh yeah, mine was 3 stories.
And they're granite stairs.
Ours aren't crazy. The outside ones are wood. Well, actually, we have stone steps outside. But the inside ones are all carpeted.
I thought that would be very bad, so thankfully I have that.
Don't fall on the steps and step because they're like marble with metal, solid metal.
Oh yeah, I remember those. And between the
Going up
steps,
those, I'm just like, if I get out,
I had my camera up there.
yeah, I do too.
Oh, did you have it this semester? I had it last semester. Who do you have for last?
Dr. D.
Oh, I love Dr. D. He's amazing.
I've gotten both. I hate Dr. D and I love Dr. D.
Do you hate Dr. D?
No. I've had both. Like people tell me they love him.
How do you hate Dr. D?
I don't know. I haven't tried to hate.
How? How?
But yeah, no, the issue I had, I was kicking a ball against the wall in my house, which I wasn't supposed to do. I was supposed to kick it against inside, but I was doing it.
Yeah, we still have like 3 more minutes to go, but do you have any question? I'm kind of wondering.
I mean,
If you have any question, I can handle. We have 3 more minutes, but if you want to check, go ahead. Continue.
It's just kind of interesting because I didn't actually like hurt. It was just like a little.
And then the ball comes. And then you were quickly corrected.
But the ball didn't hurt. So
I hope you guys know that the solution is already positive, right? You know where to look at solution. Double check it, basically.
on the homepage.
All the solutions positive. All right. I hope you know that. Let me show you. Okay. So you go to home page, solution. That's it. Everything's positive here. So before I start grading, I post the solution. Before I start grading, I post the solution. So basically, when you get the graded work back, the solution is already up. Usually. Yeah.
What? I'm curious now.
In the groups like 2 days ago, how would you know?
I probably saw it. I just so much shit to handle. I
don't know what it is, but when it comes to other assignments and other classes being graded on like hands, but whenever I see
if it was really bad, I would remember.
when I see a notification like, oh, your assignment in 01's been graded, I tend to like, I'm like, oh crap.
I didn't see it.
Is that 20 or 20?
Oh, yeah.
I got 18, I thought I did. And I could have gotten better, but I made a mistake.
Translation.
So exciting.
18, and now we'll do the 14.
Yeah. Oh yeah, that's good. That's good.
And the
82 is still
that's
80%.
because I have 20 and 2 points.
Okay, so it's 1 o'clock now.
Yes.
Looks like nobody is online today, so everybody is supposed to be in class. I hope. Let's take the in-class attendance, okay? As usual. Zoya, Zen. You don't need to go home.
Good luck.
Anthony?
You never did job on the 20. I forgot like I did. Out of him to you. I know I looked at my submission and graded it. I don't think it was units, but it was some really small stupid thing that it's like the entire process was right up until the last step, and then using one non-page or something, my answer was close.
Come on in, sit here, before I start recording, sit here. This must be there on the seat. Here we go. Okay, so that's it for today.
And had you not made that, you would have done a lot better. Well, not a lot. Could be not. And then I had a body search immediately after that. And then I got a
That's my voice. Okay, let's just get started today. So, one more time, just double checking that you already know this, but I always post the solutions before I start grading. So by the time you get graded, work back into your OneDrive shared file folder. Solution should be already up usually. So I think I would recommend first thing you do is, of course, you check your score, and then if it's like, I don't know, 20 out of 20, still, you better check your work against my work and then make sure everything's okay. Because sometimes accidentally, I give you 20 out of 20, not knowing you are doing something wrong. That is actually a tragedy, because when the exam comes, you believe what you were doing was right and doing something what you were believing, but it was not right. And then all of a sudden, 4 out of 10 on actual exam, and then that's a real issue, isn't it? Oh, professor, you gave me 20 out of 20 on this. Oh, I made a mistake, I'm sorry. This was actually the wrong solution. Then I corrected you at the exam. That's the tragedy. Okay? And then please don't do that. So score is just a score. I don't care. Are you doing the right thing or not? That's what you should care about. Okay? So please, just every work you did, please check against my solutions. Everything. Even including the one you submitted, you get full score. Please double check. Okay? Then who knows? You may, oh, wait a minute. Dr. H made a mistake, gave me full score, but I was wrong. I'm going to quickly fix it. And I'm not going to tell him. That's fine. But, I mean, if you don't do that, you're going to hurt yourself on exam, okay? So, just to make sure, here's all my solutions. And then my solution may include mistakes too. If you point out my mistake, that's probably one of the best thing you can do. I always appreciate that. Student correct professors, that's rare, but man, that's #1 thing you can do as a student. Every professor appreciates that kind of stuff. Okay, all right. Okay, so new updates, I don't know. We don't have any new updates, so we keep talking about energy principle. We get stuck on Bernoulli. We need something not Bernoulli, but something kind of we can use. Displacement of Bernoulli, we are seeking for that. So let's continue seeking by employing energy principle, conservation of energy, which is essentially thermodynamics first law. And then this week, of course, you should probably start finding a good project partner for phase 1 at least. If you don't like your partner, you can basically break up and form a new team for phase 2. But at least for phase 1, you should probably start looking at your teammates. It's limited only for the same section, so please do not try to reach out to the other section of battle. You cannot sign up for that. Okay, so you still have time. This is due noon on Friday. So noon on Friday, I'm going to rock the Canvas team function, well, Canvas and a group formation function. So you can no longer assign or sign up or anything. If your name is not listed part of the team of 1 to 6, you're not going to work on phase 1 of the project. Okay, so everything is crystal clear. So please work on it. Okay, don't wait until last minute trying to quickly form the team. That's usually introduction to disaster. Okay, so please act as early as possible, or you can wait until last minute. Who's still there, kind of thing. You can do that if you choose to. Okay. Any question about the project phase one? Project phase one due is going to be announced, and then it's negotiable, of course. Okay. All right. So today, let's take a look at what we did in last class. So last class, we started to basically try to search for what is the equivalent to Bernoulli, but it's not quite Bernoulli because Bernoulli's equation is limited only for low speed, which is specifically talking about less than 0.3 Mach number. And then now one thing which is completely different from low speed to high speed is, of course, as you see, you take a look at specific volume of a moving fluid, which is higher speed moving fluid. It just keeps changing its volume. It's called specific volume. Is not a constant. That means density is not a constant because density is an inverse of specific volume. Okay? So obviously this kind of process is always involved. Expansion, compression, which is essentially thermodynamics term. It's a moving boundary work. Moving boundary work. So as it expands and shrinks, do you think the temperature of this small tiny mass of volume change? It changes. So, okay, well, temperature change means, do you think the internal energy contained within will change?
Yes.
Yes, of course. So that's what we found out. Because of this work process, this is the moving boundary work. If this is going to be involved here, obviously the internal energy contents will be different at each location of the high-speed flow. So we want to include that analysis. And then hopefully we come up with an equation which can replace Bernoulli's equation in high speed. Okay, so that's what we looked at. And then starting point was, do you remember that starting point? We started from the first law of thermodynamics. Obviously, this is first law of thermodynamics. I keep forgetting to connect up this. Sorry about that. So, so we started from first law of thermodynamics. This basically simply says that, well, this is a heat transfer, this is work transfer, added together is balanced up against internal energy changes. That's a very simple deal, and then we did something. So we introduced moving boundary work, and then plugged back into the first law of thermodynamics, and we came up with first law of thermodynamics in terms of internal energy to begin with. This is equation 1, okay? So this equation, basically, if you try to look at it, the key term is this, delta Q. Delta Q is heat energy transfer per unit mass, okay, is equal to change of internal energy plus something called PdV, pressure times, this is the differential change of a specific volume. That's something we are talking about. This is a change of specific volume because of the pressure. It just keeps shrinking and expanding kind of thing. So those two things added together is going to be the external application of like a heat exchange due to temperature change. This is the heat energy transfer involved. Now, starting from here, we introduced a new variable, something called enthalpy. Okay, so enthalpy is a combined property, two things combined. Enthalpy is a combination of internal energy and then P over O. What's that? Then people say P over O, yeah. Pressure to density ratio. And then people call that flow work or flow energy. What the heck is that? It's very difficult to comprehend. Go ahead.
It's compressibility.
It's sort of, you can understand as an compressibility, yes, because pressure multiplied by the specific volume is called flow energy or flow work per unit mass. But it's not necessarily equal to 100% compressibility. But if you want to incorporate compressibility into your Bernoulli's equation, obviously you cannot ignore that component. And then, by the way, when you try to solve quiz 3, you use this flow energy as a trade-off against kinetic energy. I think I made a comment. Or you are making a trade-off between flow energy to kinetic energy. That's why at the test section, what is the static pressure? Minus Q. What is the static pressure at the test section of a wind tunnel? That's minus Q. What do you mean by that? That's the trade-off between kinetic energy Q to flow energy, which is minus Q. So now flow energy becomes minus Q. So you give a kinetic energy Q so that you have a wind flowing in the test section. Okay, so I hope you build one at a time. You can only build one at a time. You cannot jump right into it and say, hey, I need a PhD by, I don't know, next weekend. It never happens. You can only build one at a time. So stay focused. So that is enthalpy, right? Okay, so enthalpy is a combined property, internal energy, and then flow work or flow energy per unit mass. So introducing that enthalpy, we derived different form of first law of thermodynamics. That's what we did in last class. So we arrived in here, first law of thermodynamics in terms of enthalpy. So we started from here, we arrived here. Both same equation, first law of thermodynamics. One is in terms of internal energy, one is in terms of enthalpy. Are you okay for that? Those are the key things. Two equations called first law of thermodynamics. We are going to pick it up and then use it to define specific heat. That's what we're going to do today. You guys know specific heat. Are you okay? We probably didn't sleep last night. Well, just to stay focused on it, okay? Trying to say something. Could be wrong things, but it's okay.
The amount of air.
Amount of air? Amount of air?
Like in the amount of like.
Amount of what? Amount of energy.
Energy. Yeah.
You can store in this small tiny mass of air. That's right. You're right. So that's called specific heat. So what's the definition, mathematically speaking? Definition.
How much energy it requires to rise by 1 degree or a differential amount of Q.
That's right. So this is the definition, mathematically speaking. Okay, so this is called specific heat. How much energy transfer needed for a 1 degree change of temperature? So this is actually measurable quantity. So if you pick up any substance such as air, water, could be a rock, could be, I don't know, hydrogen or something. You pick up those substances and then you can measure, literally you can measure specific heat. So how much heat transfer is needed to make a change of 1 degree of temperature? That's how much energy you can store in this substance. Now, of course, this is material property. Air comes with certain value of specific heat. I can tell you how much. Air has got specific heat, which is 6006 foot-pound slag ranking, or 1004.5 joule per kilogram K. Here, I said it. Well, you have to memorize? Well, you don't have to memorize because it's so easily figured out if you know what is specific heat. We're going to cover that later. But the specific heat value is a material property. Air comes with certain value of specific heat. Get that? Now, the question is, how do you measure it? Okay. So it comes with a condition to measure the specific heat. When you measure the specific heat of air, you have to employ certain method. One method you can employ is you are going to put your air inside of the rigid tank. Rigid tank means volume never change. Okay? Then you stick your thermometer in it. Then you keep monitoring the temperature until the temperature becomes 1 degree different. Then you keep adding the heat energy. You heat up and heat up and heat up and heat up. The amount of energy required to increase the 1 degrees of temperature under the condition of rigid tank constant volume That is called CB. Specific heat under the constant volume condition. Lowercase b, because volume constant means specific volume is constant too. Specific volume is how much volume do you have for 1 kilogram of air, right? So this is called CB, constant volume specific heat. So this is one definition of specific heat. You understand that? There's also another way to measure the specific heat. Let's skip to the next page. So this is another way to measure the specific heat. You can put your air into, hey, here we go. This is a classic example of thermodynamics, which is the piston cylinder configuration, weightless, frictionless, no leak. You can just put the air in it, but it's free to expand, obviously. So you keep adding the heat energy, you heat up until you see the 1 degree change of temperature, you just let it expand. If you let it expand, means that pressure of this thing stays constant, right? Volume changes, but the pressure stays constant. This is called constant pressure specific heat, CP. Here we go. So there are two definitions for CPs, fundamentally different because this is different way to measure the specific heat. Do you understand those? Very, very important. This is called CP. Oftentimes, error, we choose CP. There's a reason for it. Of course. This is CB, constant volume, specific heat. This is CP, constant volume, specific heat. So let's just take a look at one by one. So this is the specific heat at constant volume. Definition of CB is, of course, delta Q, amount of heat transfer, divided by differential change of temperature under the constant volume specific heat. So this equation actually tells you the equation like this. By knowing CB, like I said, CB is a material property. Air comes with certain value of CP, sure. So if you know, let's say, if you know CB value of this classroom, okay, you can relate temperature around here happen to be higher than temperature around here because the person's sleeping and the professor's kind of mad. So this is kind of hot zone and this is kind of cold zone, right? Okay. Do you think the energy is different? Of course.
Yes.
So okay. So do you think the heat exchange happens in between those two?
Sure.
Let's say because I keep yelling at, putting my energy or heat exchange, temperature is higher. This temperature lower because this person is so cool. So you can relate that. You can relate those things. Okay, by using specific heat, you can relate the temperature change to amount of heat transfer you did. Similar here. Okay, using CP value instead of CB, you can relate the temperature change to the amount of heat exchange you did. Okay, so this is the starting point. So let's just take a look at constant volume heat addition process. This is the constant volume heat addition. So this is rigid tank. You put the air in, and then you just keep adding the heat. You just keep adding the heat. Heat is added. Delta Q is happening. Volume is constant. You just keep heating up and heating up and heating up. That's the situation. Constant volume heat addition process. Let's just take a look at it, okay? So now I'm going to pick up the equation right here. First law of thermodynamics in terms of internal energy. I'm just going to pick up this equation, okay? I'm going to pick up this equation and apply for a constant volume heat addition process. Okay, let's just do that. So this is the first law of thermodynamics in terms of internal energy. This is the constant volume heat addition process. Constant volume means specific volume constant. If so, what is the dB? Differential change of specific volume is, of course, 0. Oh, that means this is 0? Yeah. This is the result. So constant volume heat addition process. What are you talking about? This is the rigid tank. You just keep adding the heat, delta Q. And then you basically say that delta Q, the amount of heat you added, is going to be completely converted into the change of internal energy. Delta Q is equal to dE, is that correct? Simple as that, because the volume is constant. First law of thermodynamics basically says that the amount of heat you added to the constant volume heat addition process is internal change of internal energy. Then you can combine this equation with this. This and that combined. You're going to have this equation, okay? So this is conclusive equation here in this page. dE is equal to CB dt. This is actually quite important equation. This equation actually relates temperature change into internal energy change. If you know the specific heat under the constant volume process, since this is material property, if you are given material property of specific heat, you can relate the temperature to the internal energy. High temperature, of course, higher internal energy. Lower temperature, of course, lower internal energy. You can say those things using this equation. Go ahead.
I just answered my own question, thank you.
Okay, good. Did I answer?
Yeah.
Okay, good. So one more step important here. Okay. Now, this seems to be great news. However, the problem, specific heat is not a constant. It changes. And you go like, oh my, oh. It changes. It's not a constant. It is constant in a range of temperature only. In other words, room temperature zone, right? If you're talking about this classroom, yeah, specific heat is 6,006, 1,004.5. Yes, it's constant value. However, if you are dealing with high-speed flow field, where compressibility kicks in, temperature changes kind of severe. So from here to there, specific heat will be different value. So I'm going to rewrite this equation. dE is equal to CB. CB is going to be a function of temperature, dt. CB is a function of temperature. This is the concept of thermally perfect ideal gas. This is still act like ideal gas, but you have to keep track of the specific heat within the flow field as a function of temperature. People who took thermodynamics, have you ever done this kind of problem? Did you look at the property table of specific heat as a function of temperature?
Yes.
It's usually a polynomial function or something, right?
Yeah.
That is thermally perfect ideal gas model. You can still model pressure, density, temperature within the flow field, but keep that in mind. Specific heat is not a constant. Thermally perfect ideal gas. Go ahead.
So specific heat not a constant, but the CG is constant since it's constant volume.
Let's move on to CP. Is that your question? CP is not a constant, right? What's your question, by the way?
I was saying CB. I was asking if that was a constant. CB.
CP is constant?
Yeah.
CP is not constant, I'm saying. So this is a function of temperature.
Oh, okay.
CP is not constant, of course. Only constant-ish throughout this range, which is called room temperature.
Yeah.
Go ahead.
Is that what we would call calorically perfect?
That's right. In the room temperature zone, CP doesn't change much. So we can assume
Constant.
it is constant. That's called calorically perfect ideal gas model. Okay, go ahead.
Okay, so you said the specific heat is based off of a change in 1 degree temperature.
That's right.
Does it matter the different units because
Different
so
units.
the different a 1 degree temperature in what unit?
Absolute scale or relative scale?
Delta is same. Absolute scale is measured from absolute zero. Relative scale is measured somewhere here, but the delta is same. Delta t is the same, scale is wise. Yeah. Okay. Okay.
Is CV only constant just at room temperature range, or is there like ranges in general?
You're gonna find out in classroom examples. Stay focused. Okay, you're gonna find out those things. So let's just move on. Sorry about that. I didn't directly answer your question, but you're gonna find out. Guaranteed. Next thing is CP. We're gonna do the similar thing. This is the pressure constant heat addition process, of course. Piston cylinder. You let it expand, but let's make the pressure constant. Okay? So we're going to do the same thing. We are going to pick up the first law of thermodynamics in terms of enthalpy. Remember, this is the equation we derived in last class. In terms of H, enthalpy is involved. By the way, what is enthalpy? What is
Internal
enthalpy?
energy plus flow work.
E plus what? Something.
Flow work.
Flow work. Flow work is essentially P over rho. Maybe P multiplied by specific volume, P and
Specific value.
that's right. So internal energy plus this thing combined together is enthalpy. Remember that? Okay. So let's go through the same process. This is constant pressure heat addition. That means P is constant. dP is 0. Oh, that means this is 0. Yes. So equation basically becomes whatever the heat added to this constant pressure heat addition process is, converted 100% change of enthalpy. What is the change of enthalpy? It's the two things combined thing. Obviously, if you add the heat for this type of piston cylinder configuration, okay, obviously internal energy increase, temperature increase. At the same time, you create the work. Those two combined is enthalpy, right? So if you add the heat for this kind of configuration, two things happen. Of course, temperature goes up, creating work goes up. Those two combined is called what? Enthalpy. That's right. Okay, that's what we are seeing. So now we are going to combine this relationship together with this relationship in the previous page. And you're going to come up similar equation we have here. So let me just draw a conclusion here. Similar equation dH is equal to Cp dt. Okay. So this basically relates the temperature to enthalpy. Go ahead, question?
Yeah, that symbol that's in front of the Q, is that supposed to mean change?
Huh? Sorry?
For the symbol that's in front of the Q, does that mean like the change in heat or something?
It's an infinitesimal change, yeah.
Okay.
It's a heat transfer.
Yeah.
Heat transfer is a change. Yeah. How much energy you transfer to. Yeah. That's delta Q. Okay. So once again, bad news. This Cp is not a constant.
Is it a function of?
It's only, it's a function of temperature. So here we go. dH is equal to Cp as a function of temperature, dt. So you got similar equation, thermally perfect ideal gas. Okay. So let's just summarize here. So thermally perfect ideal gas means you can relate the temperature change to the enthalpy change if you know the value of specific heat under the constant pressure. However, this is not the constant. This is kind of constant under this temperature range. That's called canonically perfect ideal gas. Similar here in the previous page. Thermally perfect ideal gas means if you know the information of specific heat under the constant volume, you can relate the temperature change to the internal energy change. Problem is, this is not a constant function of temperature. It's called summary perfect ideal gas model. So problem is, this is kind of similar to what kind of equation you've seen in the past. It's kind of similar. It's a governing principle. Hydrostatic equation is an equation like this, differential form, right? Oh, Euler's equation, oh, it's a differential form, right? This is also differential form. You don't like this form because you cannot plug in the value, get the value out, kind of thing. So you have to do something. What do you do?
Integrate.
Integrate. Well, yeah, integrate both ends, but this is not a constant.
CVs.
Let's assume this constant. Then you can finish up integral calorically perfect ideal gas. Okay? So always starting from here. Now under this range of temperature, let's assume it's constant, just like Daniel Bernoulli assumed here. Let's assume density constant. Let's finish up integral of Euler and get the Bernoulli. That's the same thing happening here. So you're going to get calorically perfect ideal gas, assuming this is constant value of a given range of temperature, typically called room temperature. Right? It's always kind of weird gray zone. Room temperature, what the? Room temperature is room temperature, kind of. It's not the high temperature. So calorically perfect ideal gas, let's assume Cv is constant. Now, this constant value, I know I can tell. No, I don't know Cv, actually Cp, because I oftentimes use only Cp. So same here. Calorically perfect ideal gas relates H and T if you know Cp. If the Cp is constant, 1004.5 joule per kilogram Kelvin, or 6006 foot-pound slag ranking. Okay. How did I get that? You're going to find out in your homework. Okay. Prepare to derive the equation to have the Cp value. It's your homework. It's easy. Don't worry about it. Any question here? Go ahead.
What do you mean by the range? Is it like plus minus?
Yeah,
10
let's find
range?
out. A little bit later. Just be patient. A little bit more. You're going to find out. Don't worry about it. Okay? And then there's a relationship between Cp and Cv. If you know one of them, you can tell the other one. This is the relationship between Cp and Cv. If you know Cv, just add the gas constant of air. Do you know gas constant of air?
17 and 16 foot-pounds.
17, 16 foot-pounds slag ranking. What? 287 joule per kilogram K. You know gas constant of standard air. If you just add that to Cv, you can get Cp. We're going to derive this relationship also later. Just wait for a second. Okay, go ahead.
So I see it says calorie perfect ideal gas relation, but could you use it if it wasn't a perfect relation? So it was more thermal?
You are going to introduce, of course, errors. Obviously, the air is going to store a different amount of energy if it's a high temperature zone.
Right.
So you're going to introduce the error in your simulation or analysis.
Okay.
Yeah, that's right. Yeah.
And then for the calorically perfect, is that H equals Cp times the change in temperature?
No, this is temperature itself because you integrate it. This is the temperature. Let's say this is 25 degrees C. What is the enthalpy here? You can compute it. Right? Isn't that great? Yeah, because it's calorically perfect ideal gas. It's the temperature itself. Great. That means if you know temperature, you know the value of enthalpy. And if you know the temperature, you know the value of internal energy. Cool, isn't it? But it's called calorically perfect ideal gas. And then if Cp is constant and the Cv is constant, you can take the ratio always. And that ratio is always about 1.4. This is called specific heat ratio of calorically perfect ideal gas. Have you ever used this value 1.4?
Yes.
It's used for speed of sound. Okay. So we're going to later take a look at how the speed of sound equation comes up. We're going to derive that equation once again in this class. Anyway, go ahead.
Does gamma equal 1.4 only when Cp and Cv are calorically perfect?
That's right.
Okay.
If it's somebody perfect, you can
If
never
they're
say that.
constants in
Yeah, that's right. Correct. But it's about 1.4. It's not quite 1.4. Okay. So that is two different kind of models we talked about. Okay. Summary perfect ideal gas means that we have a knowledge of a specific heat. However, you cannot treat it as a constant value throughout the flow field. This typically happens for high speed. In other words, okay, Mach number 1.05, yeah, okay. Yeah, it's calorically perfect. Probably. How about 2.5? Still. How about 5.6? Oh, no. It's not even, I mean, it's not even supersonic, it's a hypersonic. You can never say it's an ideal gas anymore, and it's not hypersonic. Okay, so there's a crystal clear difference between subsonic to supersonic to hypersonic. So subsonic is usually, you can safely assume this is calorically perfect ideal gas, subsonic. And the supersonic is usually, well, yeah, it's still perfect gas, but can I assume it's calorically perfect? No, not quite. It's probably thermally perfect. You can still use the relationship between pressure, density, temperature, but let's not assume specific heat is constant throughout the flow field. It's supersonic. If you go beyond like Mach 6 or something, it's called hypersonic. Now it's no longer ideal gas. That's what we usually treat the aerodynamics. Okay, so that's quite important. So in AE301, we are going to focus on calorically perfect ideal gas mainly because we are talking about flow speed, subsonic. Typically, this is the truth. Specific heat ratio Cp over Cv is usually 1.4. We're going to use that and use that information to find out speed of sound. And this is okay, probably subsonic to the low supersonic. Okay. There's always gray zone, but you're going to find out later on. Okay. So let's just take a look at this example problem. If you're sleepy, pick up your calculator right now, start punching numbers rather than sleeping in the class. Let me repeat. If you're sleepy, pick up your calculator right now, start punching numbers with me. You are wasting tons of money by sleeping in this class. You have to realize it. Do you understand that? Okay, let's move on. So, you are sleeping because you don't want to understand. That's what it is. Okay, that's all right for me, but it's going to hurt you. Not right now, but possibly a month later, before you graduate, it's going to hurt you. Do you understand that? Let's not do that. Okay, so explain the difference between thermally perfect and calorically perfect ideal gas. Well, you know, if you're not sleeping, you go like, duh, I know that, right? Now, if you're sleeping, you have no clue what I'm even talking about. Now, you're already making a difference in your life, right now, right here. Okay, so what's the difference?
Temperature is constant.
No. Temperature is constant? Who the hell said it?
The thermal.
Thermally perfect ideal gas is temperature constant? No.
Only perfect gases have a constant,
Constant.
function of Cp.
Okay, calm down. Come on. So just a try. Joshua was raising hand. Go ahead.
I was just going to say that it's calorically perfect. We assume that specific heat is constant. It's thermally perfect. We assume that it can be made as a function of temperature.
Perfect. That's right. So I'm not going to write anything here because you guys know that. So part B, let's do that. For calorically perfect ideal gas, that means you assume that the specific heats are constant. Like I said, part B, okay? Calorically perfect ideal gas means Cp is constant, which I know the value. Cp is constant, which is 1004.5 joule per kilogram K, or 6006 foot-pound slag ranking. I only know Cp. I usually don't know Cv because I can figure out the others really easily. So this is constant. Constant specific heat. This is called calorically perfect ideal gas model. And then of course you can tell by taking a look at gamma equal to 1.4, which is equal to Cp over Cv. So once you know Cp, you can get Cv out. If you know Cv, you can get Cp out. So you don't need to know both. This is also calorically perfect ideal gas. Now let's just take a look at definition once again. Recall definition of internal energy. If it is calorically perfect ideal gas, E equal to CVT. We just learned it, right? Because Cv is constant, you can relate temperature to the internal energy. And H is equal to CPT. Well, if the Cp is constant, you can relate temperature to the enthalpy. That's right. And also recall, somebody please recall, what is the definition of enthalpy?
Internal energy plus flow work.
Rho work, PB, right? Or P over rho or P times B, either way, right? So what do you know? You know what E is. You know what H is, right? E equal to CPT, H equal to CPT. So CPT is equal to CBT plus, what's PB equal to? Is this an ideal gas? Right? Is this ideal gas? What, yes or no?
Yeah, it is.
This is, what? Is this ideal gas, yes or no?
No.
No?
It's the calorically perfect model of an ideal gas. So
That's right, ideal gas.
Oh.
So PB equal to
I was
what?
gonna say, this is
Rho or
no.
Rho or T.
No. P equal to RT. PB equal to? P equal to rho RT. PB equal to
RT.
RT.
Yeah.
RT.
Over M.
That's right. So P equal to rho RT. Rho is inverse of B. So PB equal to RT. Is that right?
Yes.
Yes.
That's what this thing is. So let's cancel out the temperature. Here we go. That's the relationship between Cp and Cv. Okay. Here we go. So once you know one of them, you can get the other easily. This is the relationship of Cp and Cv calorically perfect ideal gas. Any question here? It's actually very quick coverage of thermodynamics core concept. Go ahead, question.
Do you get rid of density in that equation?
Density is already included here. This is inverse of density.
Oh.
Yeah, it's already included. Yeah. Yeah, density is here. Inverse of density is B. Yeah.
Okay.
Yeah, that's right. Anything else? It's actually a good question. I appreciate that. Anything else? So now you are ready to go. Let's discover the alternative to Bernoulli. So let's just recap what we did. Okay, so this is Bernoulli, right? Bernoulli's equation in aerodynamics form P plus 1/2 rho B squared. Actually, in terms of fluid mechanics, you have to add one more term, right? Hydrostatic, gamma times Z. Yeah, is equal to constant, right? Let's call this constant 1. Well, actually, yeah, let's not do this. This is P1 plus 1/2 rho B1 squared plus gamma 1 Z1 is equal to P2 plus 1/2 rho is constant, right? B2 squared plus gamma 2 Z2. This is Bernoulli's equation coming straight from fluid mechanics. Let's do one thing. Divide both sides by density because we assume density is constant. We can do such a thing. P1 over rho plus B1 squared over 2 plus, what happens? Gamma is rho G. Rho 1 G. G is constant. So if you, yeah, rho is constant. Sorry. Rho is constant. Let's assume G is constant. So this is GZ, isn't it? So this is going to be G times Z1, isn't it? G times Z1. Yeah, I guess so. This is P2 over rho plus B2 square over 2 plus G times Z2. Have you ever seen this equation?
Yes.
What's this? This is also Bernoulli? Really? Oh, I see lots of differences here. Because Bernoulli's equation for the first form is, this is basically saying something, right? Pressure is conserved. That's what this equation says. Okay, along a given streamline, static pressure plus dynamic pressure plus hydrostatic pressure, if you add it together, it's going to be constant value. That's what you call Bernoulli's equation. Then if you believe in it, this is my Bernoulli's equation. This is pressure is conserved. Then I go like, really? Is that only knowledge of Bernoulli that you have from fluid mechanics? My challenge is here. So this is nothing. I just divided by constant density. What's this? And what's this? And what's this? B squared over 2. What is it? Kinetic energy. Good for you. How about that? Potential energy. Internal energy, you say? Internal energy? I mean, have you ever seen this one?
It's PV.
It's what?
Just PV.
PV. What's PV?
PV.
What kind of energy? Flow energy. So this is conservation of energy along a given streamline moving fluid. You basically says that along this streamline, energy is constant. What is that? First off, thermodynamics. Energy is constant. Energy can be broken down into 3 forms. Flow energy, kinetic energy, potential energy. One energy form is completely missing. What is it? Think about that. People are so lazy, you just don't miss one thing. What is it?
Internal.
Internal energy is completely dropped off. Why is that? Because it's essentially the same thing. Who cares about the temperature change from here to here in low speed? Who cares about the change of internal energy from here to here in low speed? People know that, hey, it's the same thing. Why do we even care about it? That's why internal energy is missing here. Because E1 is exactly equal to E2. You can drop it, right? That is the source of issue of Bernoulli. What if we include those two? We can apply Bernoulli for high speed. That is the secret. So we're going to find out those things, okay? Stay focused on. If you come in here and sleep, you don't have to show up to the next class, really. It's a waste of time because you don't get it anyways, okay? This is not the book knowledge. It's all about you understanding the core concept of what is Bernoulli really about, okay? So stay focused on. We're going to stop here today. As you come back on Friday, we're going to finish up this process. Here we go. We have alternative to Bernoulli. We can use it for the 0.3 Mach number correct. But not yet, not there yet. So stay focused. We're going to get there on Friday. Any questions? Question, go ahead.
So is that scope considered then Bernoulli?
This is Bernoulli. I did nothing else. I just added, ignore the terms.
Right, yeah, so it is some Bernoulli.
This is
Next step in the project is probably
Yes.
to try
In terms of energy.
I'm predicting things.
Now you want to include the energy. Go ahead.
I'm predicting
That's right.
now.
All right. Have a wonderful day. Come back on Friday.
Yeah.
So A3 will probably on Monday.
Those two assignments, one we do on Monday, one we do on Wednesday. I think it's quiz homework, I think it's homework quiz.
Either way,
It's not gonna be fun.